All right, let's do it.
Oh, okay.
Again, everyone needs to open up their RStudio. Click over here for the project, 5065. Then click on the Get tab. Click on the blue arrow to download the material on week 4. And then go to Session, Set Working Directory, Choose Directory, week 4. Choose. It should say Set Working Directory to week 4 in your console.
Yeah.
Question?
Yeah.
Everybody able to do that? Okay, so this week we're going to talk about continuous probability distributions. And speaking of things which are continuous, continuously have to mention this, but not that long, so we'll move on. Last week, defined the probability of knocking down X out of N pins in bowling with the augmented probability mass function where kappa was some non-negative integer, which we gave a Poisson prior to, that has expectation m, which reflects the bowler's inability. So when we use these probability mass functions to simulate our frames of bowling along with the bowler's kappa, the probability of knocking down X pins depends not only on n, which we saw week 2, but it also depends on how bad at bowling the bowler is, which is represented by kappa. And we've talked about bowling for a while now, and we'll continue to do so, but we should keep in mind that this is really just a metaphor for demonstrating the mechanics of how Bayes' rule and conditional probability can be used. You can think about bowling as a metaphor for success on n tasks that are not independent of each other, but you get 2 chances to succeed. And in that sense, it's a metaphor for a lot of things that we would actually want to do in social sciences. So, athletes have ability that can be represented with a parameter. Students have intelligence that can be represented with a parameter. Employees have productivity that can be represented with a parameter. Businesses have profit that can be, the capacity for profit that can be represented with a parameter, etc. And so we're doing this with bowling because it is fairly simple, but as a way where we can go through the steps. And so we used Bayes' rule to calculate the probability last week that kappa was 3. If prior expectation was 8.5, but we observed data such as x1 is 8 and x2 is 2. But like I said, that was kind of a weird way of doing it, although it was admissible, because when we're modeling stuff, we typically take parameters to be continuous rather than discrete. So last week, kappa could only be a non-negative integer. It was discrete. That's technically legal. It's just no one would do it that way. All right? So if you've got your working directory set to week 4, you should be able to source up bowling.r and get the 4 things that we defined last week. PR is this R representation of this function here. has kappa, which defaults to 0, in which case, by default, we get the same thing as week 2. Omega, which is the integers between 0 and 10, is the sample space for bowling. R is some number like 10 million. And frames is a tibble of R rows that has 3 columns, kappa, x1 and x2. Right? Everybody remember that? Okay, good. So the goal for this week is to extend what we have learned about probability and discrete random variables to the continuous random variable case, and we want to apply Bayes' rule in a situation in which the parameter is continuous even though the data can continue to be discrete. And we want to start to investigate when ancient calculations remain feasible with continuous random variables versus when do we need to do more modern calculations in order to get an answer. All right, so let's do it. So start off, review question almost. Using the frames tibble, how would you compute the probability that the number of pins knocked down on the first roll frame of bowling is less than or equal to 8, irrespective of kappa? Conditional on n equal 10, of course. It's the first roll frame of bowling. What code would you use to compute that marginal probability x1 is less than or equal to 8?
Um, I think it's summarize parentheses frames prob equals PR x1 less than.
Well, that would almost be the ancient way. How would we do it the modern way? Just using our database, 10 million frames of bowling. Marginal, unconditional, irrespective of kappa. So we've done many times what's the probability that x1 is equal to 8 using frames. How would we tweak that for the probability of x1 being less than or equal to 8 using dplyr syntax? A query to our database of 10 million frames of bowling.
Maybe you have you filter x1 less or equal to 8, and then you summarize maybe probability equals n divided by the 10 million.
That would work, yes. But that is a more complicated way of doing this without the filter. Just summarize the proportion of times where x1 is less than or equal to 8. But filtering frames based on that condition and then in parentheses over r would also yield you the answer 0.558. But usually when we use filter, we're doing it in the context of a conditional probability. That's what we've done in the past. So we'll do later today. So I would say this is preferable. But I would also say that this is not difficult. Should not be difficult at this point. Nor should it be difficult to calculate this probability exactly using the PR function. But how would you do that? Yeah.
We just sum like
Sum.
and then like TR and then in the parentheses just like set 0 to 8 and
0 to 8.
yeah, that's supposed to be
Like that?
yeah.
Yeah. Because that yields the same number. Ancient way. So the probability that a random variable is less than or equal to some number in the sample space and the discrete case can be derived from the probability mass function in using the disjoint special case of the general addition rule. You can't knock down both 5 and 6 pins on the same roll of the first roll of a frame of bowling, so those are all disjoint. Consequently, we can just add them all up, don't have to worry about any double counting to adjust for. All right? So those are questions pertaining to the so-called cumulative probability. And if we have a probability mass function, a discrete sample space, may depend on some parameters, known or unknown, theta, then the so-called cumulative mass function is the sum of the probability mass function from the smallest value of the sample space up to and including x, which is what we effectively did here and implicitly did there. In some cases, we can simplify that summation, like analytically. In other cases, we can't. Doesn't really matter which. But actually, in the case of bowling, let's say kappa is 0, this cumulative mass function simplifies just to 1 minus the logarithm of base n plus 2, evaluated at n plus 1 minus x. And so we can make that cumulative mass function by evaluating line 1 there. And if we then stack the cumulative mass function on top of the probability mass function, you can see that they're equal in the case of 0. So that would just be the accumulation of one number. But if we add 0.384 to 0.035, we get 0.0734, the probability of less than or equal to 1. Same thing with all of those. So the cumulative mass function can be seen as the cumulative sum or the running sum of the probability mass function. Yes?
Do you also do integration for this as well too? Because I know like if you're going from a PDF to a CDF, like you would integrate, but would this be the same thing here for like a PMF to a CMF?
So this is just summation.
Okay.
We're going to get to integration real soon. But this is summation because we're still talking about a discrete sample space, in which case we can add points rather than the more daunting task of adding area.
Okay.
So this is just addition. Cumulative sum of the PMF yields the CMF, no surprise, maximum value of the CMF is 1. Probability of getting less than or equal to 10 first roll frame of bowling. Literally 1. Good? Okay, so how would we use not frames, but do deterministic calculations? Probability that x1 is less than or equal to 8 and greater than 4.
Deterministically, you would just add the values for the probabilities as 5, 6, 7, and 8.
Yes. Sum those. So that would be the addition way of doing it. But an equivalent way of doing it, which is actually going to be more useful in terms of generalizing this, would be to subtract the cumulative mass function evaluated at the 8th label minus the cumulative mass function evaluated at the 4th label. So the probability that it's less than or equal to 8 minus the probability that it is less than or equal to 4 yields the probability that it is 5, 6, 7, or 8. And again, that's the same number. So I would say the addition way is probably a little more intuitive and direct. But the subtraction way is what's going to give us the ability to generalize this for the aforementioned continuous random variables. We good here? So now, like I said, if we let omega, still the sample space, but it's now an interval, has an infinite number of points. Each of those points have 0 width. Could be an interval like all real numbers, all positive real numbers, all the numbers between A and B, excluding the endpoints, all the numbers between 0 and 1, excluding 0, including 1. Any of those intervals are going to have an infinite number of points in them. And we can define a function for the probability a continuous random variable capital X is less than or equal to a given value, little x, and call that function the cumulative density function. It's a function. It's got to be a unique rule mapping from some input space to some output space. The input space is, again, the sample space omega. The output space is the numbers between 0 and 1 inclusive. Consequently, we can interpret a CDF as outputting a probability that a random variable x is less than or equal to some value little x. And there's really no difference between a cumulative mass function and a cumulative density function conceptually, except to emphasize on whether the sample space omega is discrete or continuous. But because there's no real conceptual difference, I'm going to use the letter capital F for both or either a cumulative mass function or a cumulative density function under the presumption that it's going to be clear from the context whether I'm talking about a continuous or a discrete random variable x. Okay. So this is barely different from what we've done with bowling, but now just continuous rather than discrete pins. And as an example of a cumulative density function, this time going from actually all real numbers, although just -3 to 3 is shown here. So this is a cumulative density function. Cumulative density functions are always increasing functions because the probability that the random variable x is less than or equal to x is always going to be a smaller number than if little x was a little bit bigger. So cumulative density functions are increasing, and cumulative density functions from all real numbers on the horizontal here to the 0-1 interval on the vertical here often have this S-like shape to them because the cumulative probability cannot be less than 0 and it cannot be greater than 1. So you get this kind of squishing at the edges where the cumulative density function becomes almost flat as you go toward infinity in either direction. But it's going to have some part in the middle where it's kind of steeply increasing. So a lot of cumulative density functions look like this one, or roughly this one. Right? Good? Good. All right, probability density functions, aka PDFs. So if we want the probability continuous random variable capital X is both less than or equal to X and greater than A, we can do what we did before, which is evaluate the cumulative density function at X, subtract off the cumulative density function at A, the same way that we did or could have done for discrete random variables such as bowling. Can also do that continuous. So the probability that X is between X and A is the difference in the CDFs evaluated at X and A. And if we let X be equal to A plus H, we can express the slope of a line segment connecting X and f of x with the point A and f of A. So if you imagine those 2 points and the line segment between those, the slope of that line segment would be the rise divided by the run. But if x is equal to a plus h, then x minus a is just h here. So you have rise in the numerator, run of h. And the denominator would be the slope connecting those 2 points. And if we then furthermore let h approach 0, then this ratio that is our slope is the derivative of the CDF with respect to x, the rate of change in the CDF as x changes a little bit, aka the slope of a CDF at the point x, aka the tangent of a straight line that intersects the CDF locally at one point. So, if you think about a tangent line over here, just barely grazes the CDF at one point. The slope of that tangent line is the derivative of the CDF at that point. And the derivative of the CDF with respect to x is called the probability density function, more often known by its acronym PDF. It's denoted by me, at least, a lot of books, little f. PDF is positive because the CDF is always increasing. Or at least it's non-negative, but usually it's just positive. Right? So because little f is the derivative of big F, little f is a function from the same sample space omega, but it has a different output set, all positive real numbers, not restricted to be between 0 and 1, and consequently, little f, the PDF, does not yield a probability. It yields the slope of the cumulative probability. But nevertheless, it is used much like a probability mass function is used in the discrete case. And then you can reverse things around. You can think of the cumulative density function, capital F, as the integral, definite integral, of little f from negative infinity or whatever is the minimum value of the sample space omega up to an upper limit of little x. That's going to be the area under the PDF up to the point little x.
Yes, just for my understanding, when you're saying capital F, so that's like the probability, and then the lowercase f, is that like
That's
random
this.
variable, like
Okay, so capital F would be a function like this.
okay.
The derivative of that is what I'm calling little f. It's the probability density function. The derivative of that is the slope. So this is a probability. It's between 0 and 1. The slope of a probability generating function is not a probability. It's just a slope. So this is capital F. Slope right here can be obtained by evaluating little f. Question? 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 So example of a probability density function might look something like this. Again, we have all real numbers as the sample space, even though we're only plotting from -3 to 3. Might get a curve, looks something like this. Happens to be between 0 and 1. Oh, that's messed up. That should be PDF. There. So this is a PDF, and this is the PDF of the standard normal distribution, so-called bell-shaped curve. But in fact, this PDF is the derivative of this CDF, which is the CDF of the standard normal. The slope of this at any point is given by this. And so you're often see these PDFs, but just remember, like a PDF, at least the way I'm framing it here, isn't like a primitive thing. It's derived literally from the CDF. And you don't so much see often this. Like you probably didn't even recognize this as the CDF of the standard normal distribution, even though this is the thing that it's like offspring is the derivative. This. Questions? So I've put together a table outlining the most important of the many correspondences between discrete and continuous random variables. So over here in the middle column, we have the notation assuming that x and y are defined on some discrete sample space. Over on the rightmost column, we have what is everything is continuous. And in the first row here, the cumulative probability, well, like I said, it's pretty much the same thing. So I can represent it with capital F in both cases, even though the two cases differ as to whether x is discrete or continuous. We defined last time the median in the discrete random variable, smallest value of x in the sample space, such that the cumulative probability was greater than or equal to 1/2. Same idea in the continuous case, except in the continuous case, there's going to be some number x such that exactly half the probability is less than or equal to x, and exactly half the probability is greater than x, and we call that x the median. And since the cumulative density function is increasing, it's going to have some inverse function, a function from the vertical to the horizontal, so that we can evaluate that function at 0.5 by going over the curve down to obtain the median, and the median of a standard normal is 0. But still, pretty much the same idea, except now it's not greater than or equal to half, it's exactly a half. And we can define the rate of change in the cumulative mass function as the slope of a line segment connecting two adjacent points. But in the case of continuous random variable, we have to be taking the derivative of the CDF and evaluating it at the point x. Last time we defined the mode as the maximum value in the sample space that maximizes the discrete probability. Analogous in the continuous case, what's the value of x in the sample space that maximizes the probability density function? So as we can see here, probability density function of the standard normal is maximized there, 0. So although the median and the mode are different concepts, the median and the mode are both 0 in the case of a standard normal random variable. But again, the mode is not that important a deal in Bayesian analysis, but the median certainly is. We can evaluate the expectation of some function g, where g depends on x, and x is a random variable, and because random variables are functions, functions of random variables are composite functions, or otherwise we can consider g to also be a random variable that is precipitated by x. In the discrete case, we can just do summation of points for every x in the sample space, evaluate g, weight it by the probability that of x taking that number, sum it all up, and we get the expectation of g. In the continuous case, have to do an integral over the entire sample space omega take G, weight it by the PDF, evaluated at X, integrate it over all the X's in the continuous sample space omega, and we get the expectation of G. So the G functions can actually be the same in both of these cases. But the way in which we obtain the expectation differs a bit. Here we're adding points, there we're adding area under the curve of the integrand, where the integrand is G times F. And so this is what leads Grant Sanderson to say in the video on the syllabus for this week that for the most part, you can just convert the summations in the discrete case to definite integrals in the continuous case, and that, roughly speaking, gets you there, although we could be more formal about that math. We are not going to in this course. We have the multiplication rule in the discrete case. Marginal probability of X times conditional probability of Y given X yields the joint probability of X being something and Y being something, conditional on theta, of course. Have the same thing in the continuous case, but expressed in terms of PDFs. Marginal PDF of X times conditional PDF of Y given X yields bivariate PDF of X and Y jointly, possibly conditional on some parameters. And if the multiplication rule holds, then we can extend Bayes' rule to the case of continuous random variables. So we've seen the discrete one before, again using my notation for marginalizing over X. Right-hand side of Bayes' rule in continuous case is still going to be the joint probability density function of X and Y divided by the marginalized PDF of F of Y, and the marginalized PDF of F of Y can be obtained from integrating the joint PDF of X and Y over X space, as we have here. So that, in a nutshell, is the correspondence between the major concepts of discrete random variables and their analogs in the continuous random variable case. And you might say, well, it looks like we're doing a lot of integrals and maybe some derivatives, but actually we're not. If necessary, you could certainly use an online service such as Wolfram Alpha to do those derivatives, and it would be able to do some of those definite integrals. So that's just a web service. Columbia, you can download the full Mathematica for free, so I would recommend you do that while you have the opportunity, even though I don't favor using Mathematica for teaching as much as I do open source software. But if you're an open source purist like me, yeah, you can do symbolic stuff in Python as well. It's both a Python library and a web server that has the online library that you could use. So if necessary, you could use those things to do the derivatives or integrals or whatever. But it's not really that necessary so much for this class. All these distributions has been known for decades, if not centuries. You can just look them up on Wikipedia, things like that. So, we might do one or two integrals, but we're not really going to be doing it that much in this class. We just need to know that this is the derivative of that, and the integral of this up to here is this function evaluated at there. Right. So really just need the concept of area under curve, maybe not the whole area. Well, the whole area is 1 in the case of PDF, because the CDF is bounded by 1 all the way over there. So we can do the, integral up to here if we want, or, all the way. All right. So one of the important g functions, either in the continuous, like we're doing here, or the discrete case, is random variable x minus its expectation quantity squared. So if x is a random variable, in particular if x is a continuous random variable, then g is also a continuous random variable. And if g has a continuous random variable, we can investigate what its expectation is by applying the formula. So g, x minus mu quantity squared, weighted by the PDF of x, integrated over x, and presuming that integral converges to a finite number, which it is not guaranteed to do, but most of the time in probability it does. So assuming that integral to converge, the expectation of g is special. It's known as the variance of x, and it's so special that it has its own Greek symbol, sigma squared. So the variance of x is the expectation of x minus mu squared. And so g is a random variable that is derived from x. Expectation of g is known as the variance of x. And there are some g functions that are so special that when we evaluate their expectations, they have their own names, like variance. The variance, although it is commonly used in theoretical statistics, often less practically useful than the square root of the variance, specifically the positive square root of the variance, which is sigma, and known as the standard deviation of x. Standard deviation is more practically useful because the units of a standard deviation are the same as the units of x, whereas the units of a variance are in units of x squared, which is a weird thing to think about, like dollars squared or age squared or height squared or anything like that. So if we express the deviation from the expectation in terms of the standard deviation sigma, we can talk about the thing in the original units, dollars or years or inches, whatever. Another thing that you will occasionally see is the reciprocal of the variance, which is known as the precision of x. And there was a minute where using the precision rather than the variance or the standard deviation made some Bayesian computations easier. That minute has passed long ago, but you will still sometimes see it, in particular with the Lancaster reading. So let's talk about this. In the case of the normal distribution, sample space, all real numbers. Normal distribution is conditional on mu and sigma, the expectation and the standard deviation. Expectation can be any real number, standard deviation can be any positive number, and the PDF of normal distribution looks like this. Again, the formulas for these things can look weird even if the curves they imply look normal. So the curve in this is the function little f here. E to the negative 1/2 time, or in the exponent, x minus mu over sigma quantity squared, and then all that e stuff divided by sigma and the square root of 2 pi. That pi actually is the circle thing. In R, d followed by norm, that function evaluates the PDF, so you don't have to type out the thing. in the top right. D norm has it. R norm draws from a normal distribution. So those are the main two things you need to know. But like I said, there was a time when parameterizing the normal distribution in terms of the precision, tau, rather than the standard deviation of the variance, made things a bit easier. In which case, if we just substitute tau for sigma squared in that, rearrange things a little bit, we get an equivalent expression for the normal PDF, but in terms of the precision tau rather than the variance or preferably the standard deviation. And this actually happens in the Lancaster reading for next week, which is published in 2004 or whatnot. So the standard deviation, I think, is preferable, but mathematically it doesn't matter too much. And this is the PDF for the general normal distribution. If we take the special case where the expectation is 0 and the standard deviation is 1, we get the standard normal distribution. And in the case of a standard normal distribution, it doesn't matter if it's standard deviation, variance, or precision. All of those are going to be 1. Okay? Question about the normal distribution. All right. So another core continuous probability distribution is the uniform distribution. More specifically, the standard uniform distribution for a continuous random variable x defined on a sample space between 0 and 1 inclusive. Standard uniform distribution has CDF f of x equal to x. Consequently, its derivative, the PDF, is 1, irrespective of x. So the PDF is horizontal, CDF 45-degree line. PDF horizontal, CDF 45-degree line, etc. You can draw. So we've talked a little bit already about like how do you draw from these distributions without really explaining the algorithm as to how that could be done. It can be done using a hardware directive on an Intel or even an AMD if you have into Mac or whatever. Hardware instruction, but R doesn't actually do that. It uses software code to produce pseudo-random numbers. And those are actually better because it can be done much faster. And moreover, those are actually better because they can be made deterministic, as was discussed a little bit yesterday in recitation. If you set the seed of the pseudo-random number generator to some integer right at the outset, then every time you render your Quarto document, the random numbers will come out in exactly the same order so that you get the same answer literally every time, as opposed to having to deal with the annoyances where your answers are slightly changing every time you render it. So you can sort of make the pseudo-random numbers deterministic, but still use them as if they were genuinely random. But theoretically, we could do genuinely random, which is why we know the RUnif function in R is just as good, but also, faster as compared to genuinely random numbers. So that's the standard uniform distribution. We can generalize that to a uniform distribution on any interval where B is greater than A. CDF is now x minus A over B minus A, in which case the derivative of this is just 1 over B minus A. You can draw from that by specifying the minimum and the maximum argument to RUnif. But by default, those are 0 and 1 respectively, so that you're drawing by default from a standard uniform distribution. Standard pretty much just means choose the values of the parameters that make this mathematically easiest in some sense. So standard in the case of normal, expectation 0, standard deviation 1, simplifies that a little bit. In the case of standard uniform, lower bound equals 0, upper bound equal 1. Again, simplifies this. But standard doesn't have any deep meaning. It's just whatever's easiest. That's all it really means. Questions about uniform distributions, standard or otherwise? Got a little quiet today. Question?
For the uniform, would the CDF just look like just a standard y equals x line?
In the case of between 0 and 1, yes. 45. Then the PDF would be 1. On a not 0 to 1 interval, the slope could be a little bit different, but it would still be a straight, CDF would still be a straight line, no wiggle to it. Second derivative would be 0, even though we don't really do second derivatives in a class like this. Other questions? Alrighty, another distribution, this one popularized by the Bayesians, known as the beta distribution. So again, omega, sample space between 0 and 1, has two parameters, a and b, both of which are positive. And the PDF is defined as the ratio x raised to the power a minus 1 multiplied by 1 minus x raised to the power b minus 1 divided by the so-called beta function. And the beta function is defined as this integral, basically the same numerator there, integrated from 0 to 1. And this beta function is known as a special function. You might say, what's so special about it? Well, what's special about it is it can be expressed analytically, albeit as a product of an infinite number of terms. So this pi here is the notation of the product of all this, is I goes from 1 to infinity. So we've seen infinite sums before. This is the infinite product. Now, if you were doing this by hand, the idea of multiplying an infinite number of terms together might seem daunting. However, if you're doing it on a computer, it's really not so bad. Of course, we can't get it exactly correct, if getting exactly correct requires an infinite number of terms. However, we can rather easily get it correct to 15 or 16 decimal points with a very finite number of terms. And getting it correct to 15 or 16 decimal points is way more than what we ever need. But if you needed to do that, you can evaluate the beta function in R by calling the beta function. But again, we really don't even need 15 or 16 decimal places for most purposes. But it's kind of an important idea. So if you talk to your esteemed colleagues in the math department, they might say, well, something that is correct to 15 digits means it's incorrect past this 15th digit. But we, as social scientists, or social scientists more generally, don't care if it's incorrect past the 15th decimal place. We don't even really care if it's incorrect past the first decimal place. Right? So what's necessary and more than sufficient and overkill for science is, definitely different than what is like symbolically, mathematically, the truth. Yeah. So anyway, the d beta function in R evaluates that little f. The r beta function draws from a beta distribution. Unfortunately, R does not call the parameters a and b. It calls them shape 1 and shape 2, respectively. But in any event, if a and b are both 1, then you can work this out. It simplifies to the standard uniform PDF. So standard uniform, special case, of beta with A and B equal to 1. Conversely, beta is a generalization of the standard uniform where the second derivative is not 0. So it's not just a straight line like this. It can be a curve. Moreover, it can be shown, although we're not going to show it, that the expectation of x if x is beta distributed is equal to a divided by a plus b. Moreover, if both a and b are greater than 1, which is a slight restriction on the definition, they're only required to be positive, but if they're greater than 1, the mode of the beta distribution is a minus 1 in the numerator and a plus b minus 2 in the denominator. So you might be wondering, well, what if a and b are not greater than 1? Well, then the PDF of the beta distribution is going to have this U-shaped thing to it. And so it is not going to have an interior mode. It has a trough spot. But the case of that where it's like, more likely to be on the edges, less likely to be in the middle, not so common in social sciences. Usually when we're using the beta distribution, it's going to be with A and B greater than 1, in which case it's going to have some kind of normal shape to it, but it's going to be a little bit asymmetric if A and B are not equal, and it's going to be restricted to the 0-1 interval rather than going to negative infinity, positive infinity, both directions. Questions about the beta distribution?
Yeah, I learned that the reason that most of the researchers, they prefer the beta distribution is this distribution can approach nearly any shape of the distribution, no matter the skewness, the kurtosis, or uniform distribution, U-shape, bell-shape, whatever. Is that correct?
Correct-ish. It's restricted between 0 and 1. So it's really only applicable to such random variables. But yeah, you can have it take not every shape, but a great variety of shapes in that sample space with a judicious choice of A and B, including the totally flat shape with A and B both 1. Or the symmetric shape with A and B equal, even if that's not 1. So yes, it is fairly flexible on a very narrow 0 to 1 interval. Other questions regarding how great the beta distribution is? All right. So now we need to talk about something that's closely related to Bayesian analysis called decision theory using random variables. And so according to decision theory, the theory of making decisions, to make a decision that maximizes utility, you need to follow the following 5 steps. 1, enumerate capital D possible decisions that are under consideration. 2, define some utility function G that depends on the unknown random variable x. X can actually be either continuous or discrete, but it's some random variable x. The G function can also depend on what decisions you make, or maybe some other, known quantities, but it's going to depend primarily on some random variable x. So we have G, which is our utility function. It's going to be random because x is random. Step 3, update your conditional probability distribution for all the unknowns. In this case, there's just one, x. Given all the knowns, in particular data, using Bayes' rule. So that's why there's a very close connection between decision theory and Bayes' rule, because in step 4, you need to evaluate the expectation of G. Well, what should we weight G by when integrating over the space of x? Well, we should use the conditional PDF of x given the knowns to get that conditional expectation of G for each of the D decisions that are under considerations. And finally, 5, choose the decision that has the highest value from 4. So this is called decision theory. because it's pretty much the only theory of decision making that has any mathematical basis behind it. And the mathematical basis is fairly extensive. It is a question?
Yeah, I mean, I was just gonna basically ask, this is basically like basically doing optimization then?
Maximization of expected utility, yes.
Okay.
But the expectation, well, what distribution are you using to form the weights in that expectation? Use Bayes' rule. Conditional PDF of the unknowns given the knowns. That gives you the best basis to be making this monumental decision. Despite this being pretty much the only question.
Yeah, I had a question. Because I recall in my game theory classes in the past, whenever it was a game where you don't have full information, we call the Nash equivalent of Bayesian Nash equivalent. Is this why? Because Bayesians have been.
Yeah, there's a connection to game theory as well. Even if you don't have any opponent, like it's just you making a decision or anything like that, this would be applicable. But if you're strategizing against another person, then if both people do this, and some other kind of weak conditions, such that given what the other player does, you don't want to change your strategy, then that is known as the Bayesian equilibrium.
But why is it called I mean, surely Bayesians are the only ones who deal with uncertainty. I mean, why is it not the frequentist Nash equivalent?
The Bayesians are the only ones who deal with uncertainty in terms of expressing everything in terms of probability distributions. So in the case of game theory, it's sometimes, but usually not, something being randomized. So there's no sort of Fisher game theory, even though Fisher and von Neumann were contemporaries, basically, because von Neumann was explicitly endorsing the subjective interpretation of probability. What do player A believe about players B's capability or intentions or things like that? And so because of the game theorists pretty much explicitly endorsing the subjective view of probability, it did not attract a whole lot of interest from hardcore frequentists such as Fisher, other probability theorists who are more statistically inclined of the day, who were really only interested about things that they thought they could be objective about. Whereas, there's no sense in which Prisoner's Dilemma is objective. It's just, the equilibrium is that they both admit to their crimes. Subjectively. Question?
So you can also apply this for the other distributions you were talking about as well, too?
Yeah, does not hinge on what the distribution of x is, or whether it's continuous or discrete. It's a general procedure. Only thing it really hinges on is whatever x is, you want the conditional PDF of or PMF of x, given what you do know, to be the weight function when you get the expectation of g. These are all good questions, although it sidetracks me from the point that I wanted to make, which was that despite this being pretty much the only way of making a decision that has a lot of mathematical theory behind it, it is at odds with virtually every empirical study of how people make decisions, which, as compared to this, seems ad hoc, if not ridiculous, by comparison. And so if you ask people how they make decisions, even if you ask the CEO from some giant company how they make decisions, you'll often get some hand-wavy thing of, I talk with all the stakeholders and I weigh the pros and cons, but when it kind of comes out to it, then I just go with my gut, and it always turns out good most of the time until it doesn't. and then I get fired from my CEO position because I made a bad decision. Or, a little bit more commonly, you will see, well, I, as the CEO in my giant office, call down to my like vice CEO, and the vice CEO calls down to some like junior level, entry level analyst person and says like, look at the data, give me your best guess for X. And then I take that best guess for X, I put it in G, and then I see what comes out, and I make the decision based on my best guess of X. Well, the best guess of X, more properly speaking, would be the mode of X. Like I said, in Bayesian, mode is not very important, because knowing the mode of X does not tell me the expectation of G. Take the expectation of G, at least in the case where X is continuous, I got to know an integral, not just X at one point. The junior analyst or whatever tells me is their best guess of X. But if that best guess turns out to be badly wrong, then it can always blame the junior analyst for coming up with a best guess of X that is wrong, when actually the blame lies with the CEO for not using decision theory, integrating over your uncertainty in X. Maybe not with this, but with some PDF, using the conditional PDF of X given what you know as a way to come up with the expectation, rather than taking the mode of X and pushing that through G, which doesn't even yield you the mode of G. It doesn't yield anything. It's just G evaluated at your best guess of X. So you will not really see anyone making decisions this way, despite us having a fairly simple framework for making those decisions. And if we follow these 5 steps, we can maximize our expected utility. Whereas if you just go with your gut, it doesn't really do anything, much less mathematically. But it, at best, is the same as this. And this is optimal with respect to your utility function. So whatever else people are doing, it's less optimal than this. But you got to define your utility function. Questions about that? Fairly simple. 5 steps. But the 3rd step involves a number of previous steps that we've talked about and we'll continue to talk about this semester. So now let us apply this to the most consequential decision of your lifetimes to date, and quite possibly most consequential decision of your lifetimes going forward, which was the Food and Drug Administration, FDA, decision as to whether or not to approve the messenger RNA vaccine, which is often referred to as Pfizer, which is a bit unfortunate because the science of this was done by a small company known as BioNTech. But they partnered with Pfizer to manufacture and distribute the vaccine because Pfizer had a lot of trucks and refrigerators and stuff. Moreover, Pfizer and factories. Moreover, Pfizer had a lot of experience getting other sorts of drugs through the regulatory approval process, both in the United States and other countries. So BioNTech and Pfizer formed a deal where they would jointly do this. But the science behind it was primarily by BioNTech. And Pfizer took the lead on getting approval for this from the US government, specifically the Food and Drug Administration, FDA. And they, in fact, used Bayesian analysis. How many of y'all knew that before I just told you? Nobody? New York Times must have omitted that fact.
I actually got Johnson & Johnson, so.
Okay, I don't know, that got approved, so that's good, but I don't know what analysis form they used for that. I know Moderna did frequent this. But anyway, let's talk about BioNTech, Pfizer, even if the New York Times did not. And this is going to seem a little bit weird, but it's not weird because it's Bayesian. It's weird because the FDA has some weird conventions. So let's let pi sub v be the probability of getting COVID for someone in the randomized controlled trial conducted by Pfizer who was vaccinated in late 2020, like fall 2020. And so this pi is between 0 and 1. It's not the circle thing. Similarly, pi sub c is the probability of getting COVID for an unvaccinated person in the fall of 2020. And if we define those two quantities, we can define theta as pi sub v divided by the sum of pi sub v and pi sub c, so that the so-called vaccine effect, which is a function of theta, is defined as 1 minus 2 theta in the numerator and 1 minus theta in the denominator, which if you simplify comes out to 1 minus pi sub v in the numerator and pi sub c in the denominator. And so to the extent that pi sub v is much smaller than pi sub c, the vaccine effectiveness is going to be close to 1. If pi sub v and pi sub c were equal, then the vaccine effectiveness would be 0. And what's a little bit weird about the FDA is like vaccine effectiveness is like their utility function, how they evaluate whether a vaccine is effective enough. And they have a rule, I don't know if it's a rule that's really written down or if it's just like kind of word of mouth within the FDA, that it's usually more applied in the frequentist analyses with which they have more experience. But there's kind of informal rule for vaccines that they want the vaccine effectiveness, the point estimate of it, to be greater than 0.3, and they want the confidence, or they want the point estimate for the vaccine effectiveness to be greater than 0.5, and they want the confidence interval to exclude 0.3. So that's kind of the heuristic that the FDA usually uses when approving or deciding on whether to approve a drug. But in this case, Pfizer was doing a Bayesian analysis. And you might say, well, I don't want to know the probability of getting COVID given, I don't want to know the vaccine effectiveness, I want to know pi sub v. Like if I get vaccinated, what's the probability that I get COVID? But the FDA doesn't actually estimate that. It estimates 1 minus the ratio. So it's like essentially estimating this, but not the numerator and the denominator separately. Like I would want to know the numerator, but FDA says I want to know the ratio without separately estimating the numerator and the denominator. So that seems a little bit weird, but that's how the FDA rolls. And it's like legal to do that from a Bayesian perspective, even though that doesn't seem like the greatest thing to do. But Pfizer is certainly not in the business of arguing with the FDA about the appropriateness of the FDA's rules. It just follows. So the parameter here is theta. And theta was given a beta prior, so this was actually all pre-registered. Pfizer sent a massive document to the FDA in the summer of 2020 before it even did the trial, outlining all the things it was going to do, including what its prior on theta was, which was a beta distribution with A roughly but not exactly 0.7 and B equal to 1. which was chosen, albeit not well, such that the vaccine effectiveness function evaluated at the expectation of theta was about 0.3. So at the expected prior theta, the vaccine effectiveness would be insufficient to get FDA approval. But of course, conditional on the data, we could get updated beliefs about theta. And the vaccine effectiveness, we get update beliefs about that as well. Question? Question. Okay, so A is about 0.7, B is about 0.1, and we do have a question.
So the goal for this is like, if you were to graph it, is it like to find like the optimal point where like the optimal values of like A and B are like the highest? I know this is like a case on case basis, but
Yeah.
I was just kind of curious of my understanding.
So Pfizer, I believe, wanted to do something simple.
Okay.
And they did something which I would say is overly simple, in the sense that they chose A and B such that, okay, if like the prior was true, the vaccine wouldn't get approved. So they want the approval to come from the data, or be more influenced by the data being sufficient to move your beliefs about the vaccine effectiveness over. And like, if the data were, not too different from what the prior is saying, then it wouldn't be approved. So in a manner of speaking, they did like not a weakly informative prior, but a prior that it was not favorable to them. In the sense, if you just took the prior, it would not be adequate to get approval of the vaccine in the United States or any other developed country. Really? But now we're going to do a trial, so we get data, so we get updated beliefs about everything. Still not a question. All right. Question over here.
So can I say they just arbitrarily to set the values of A and B for their purpose at the bottom line of the 0.3, and then using the Bayesian process to update their belief and see the final result?
Yeah, I would say that's adequate summarize of what I believe Pfizer said. Again, this was summer 2020. They started with the 0.3. So, okay, that's like kind of a baseline, but not adequate to get approval on the vaccine effectiveness. And then they chose an A and B that was consistent with the 0.3 value, using relatively small values of A and B so that there was kind of a large variance. So, and then they're going to get data with the trial. So if we plot the implied prior distribution, not of theta, but of the vaccine effectiveness, we get this curve here. And this is what I was saying. Pfizer tried to do something simple, and I think ended up doing something not super great. So at A and B, they would get something like this that they chose over here. But as you can see, the prior mode of the vaccine effectiveness was almost 1. So yes, at A and B, you're down here. But the prior mode of the vaccine effectiveness was extraordinarily high. And perhaps worse, we're 0.3, like here. But perhaps even worse than setting the prior mode so close to 1, you have a whole lot of area less than 0, which is mathematically possible if the probability of getting COVID given that you're vaccinated is greater than the probability of getting COVID given that you're unvaccinated. Mathematically possible, but no credible scientist would have believed that prior to the trial. It's not biologically possible, so they're not injecting you with the virus. They're just injecting you with synthetic messenger RNA. it has no ability to replicate itself. So it can't make you more likely to get COVID than an unvaccinated person. Now, there was a little bit of minor behavior argument that people in the trial, if they had some side effects, like they felt a little bit not great the next day or whatever, the people in the trial might believe that they were vaccinated, whereas the people who got the placebo wouldn't have had a side effect, so they believed that they were unvaccinated. And so if the people who believed they were vaccinated in the trial, it was like, okay, I'm going to the club now, then possibly they could engage in behaviors that were more likely to get them infected, believing themselves to be protected. But that's kind of a third order argument, whereas biologically speaking, all this negative vaccine effectiveness probability is not particularly credible. So it would have been like better had Pfizer chosen a prior that gave negligible probability of the vaccine effectiveness being negative, but not so much of like a mode here that is so close to 1. But nevertheless, that is what they did. And I'm not sure why the FDA didn't tell Pfizer to like get its act together. Like, honestly, I'm not sure why the FDA, well, I know why, but in theory, like, why doesn't the FDA do the trial? Like, why do we let the drug companies do the trial for their own drugs that they have like a massive interest in getting approval? Well, it's because the FDA doesn't get enough funding to do anything, really. And the drug companies have way more money than what the FDA does. So they just let the drug companies do their own trials. But still, like, the FDA could say, like, Pfizer, you need to do it this way, or you're not getting approval, in which case Pfizer would.
Sorry, another question. When you're saying density, is that focusing on the variance, kind of?
This is a PDF of vaccine effectiveness under the prior.
Okay.
So vaccine effectiveness is a continuous random variable. It has a lot of variance, that's true.
Okay.
It actually goes from negative infinity to 1. But, it has this kind of weird shape to it.
Thank you.
Alrighty, so let's actually do the analysis that Pfizer did. So type this with me. N equal 94 was the number of people in the trial who got COVID. So half the people got the vaccine, half the people got the placebo. Of those, Y equal 8 people who were vaccinated got COVID. And 86 people who were unvaccinated got COVID. So we can create ourselves a tibble with like 10 million draws from our beta prior all over theta, with shape 1 being A, which was 1, and shape 2 being B, which was about 0.7. Get 10 million draws of theta from your prior. And then draw from a binomial distribution with size equal 94 and prob equal theta to simulate a number of people out of 94 who got COVID despite being vaccinated, or hypothetically got COVID despite being vaccinated in our simulations. So we draw theta from a prior, we draw y from a binomial distribution given theta and n equal 94, which we're conditioning on. We then filter based on what happened in reality. So we take the rows of our tibble where the simulated number of people who got COVID despite being vaccinated is exactly equal to y, where y is 8. And then we're going to analyze that subset that we filtered in. We're going to compute the, so by filtering, we get the posterior distribution of theta given little y. We're then going to calculate the vaccine effectiveness under the posterior distribution by applying the vaccine effectiveness formula. And then on the next slide, we can see the plot here, which we'll get to in a second. But again, main steps here, draw theta from a beta prior, draw hypothetical data from a binomial distribution, conditional on the realizations of theta, filter based on what happened in reality in the data, where y was equal to 8, calculate the vaccine effectiveness with the posterior draws of theta, conditional little y, then plot them, comes out looking like, damn it, comes out looking like it got timed out from my server. Re-render. Drum roll. Should have used the smaller R. Extended drum roll. I need a fast forward button. This is going to look ridiculous on YouTube. There we go. Blah, 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 blah. Continuous beta, prior, posterior. Do all these steps. We get a plot. Looks like this over here in red. Posterior PDF of theta. Over here in green. Posterior PDF of vaccine effectiveness. And so given the data where 8 out of 94 people who got COVID were vaccinated, no surprise that the vaccine effectiveness distribution was quite high. And you may have read in the New York Times that the vaccine effectiveness in 2020 against infection was 90%. Now, that is a little bit of a coarse conclusion. What the New York Times may have meant was that the posterior mode was about 0.9. Or maybe they meant the posterior median was about 0.9. Or perhaps they meant the posterior mean was about 0.9. Honestly, not super clear, but had they done the actual analysis, they would have gotten not a single number, but rather a distribution. And the variance of the distribution reflects our uncertainty as to what the vaccine effectiveness is, even after having done a randomized controlled trial. So we were certainly not, or we should not have been sure completely that the vaccine effectiveness was literally 0.9 on the basis of a randomized controlled trial that had 94 cases of COVID. But we are completely sure that the vaccine effectiveness is greater than 0.5 or 0.3, any of these. Really, we're completely sure it's greater than 0.7. And so this was a fairly easy decision for the FDA to make, which was fortunate in the highly politicized climate that they came up with a fairly easy decision. Didn't exactly matter that much how you analyze the data when the data are as one-sided as they were. Question?
Is this how the FDA's counterparts in other countries also make decisions, or?
I don't know about every country. Actually, I only know about the United States, and even then, not that much. I know Pfizer. Pfizer had just like one trial at the time, and they used the data from that one trial in every country in like the United States and Western Europe. But I don't know what like the rules are in the EU. I don't know. Maybe. So if you look carefully, like very carefully, you might see that this red line here is almost literally on top of the black line. Black line was calculated not from the draws, but by plotting a particular beta function with shape y plus a and n minus y plus b as the parameters. And we can see we get exactly the same as the red line, which was derived from the simulations. And in fact, Pfizer's calculations could have been done and were done the ancient way, not with simulations. So if we take the binomial distribution here, which also depends on theta, so failure means getting COVID when unvaccinated, success ironically means getting COVID when vaccinated. We had 8 successes and 86 failures. And with a beta prior on theta, which has the same form as this, if we want to marginalize away theta to get the probability of y given a, b, and n, but not theta, we need to do this integral here. But if you group the terms together, you get theta raised to the y plus a minus 1 and 1 minus theta raised to the n minus y plus b minus 1, and then a bunch of stuff outside. And so it takes the same form as this integral here. And we know that that is the beta function. Consequently, this integral can be done analytically to get a denominator of Bayes' rule that takes that form. And then if that is the marginal probability of y, we can evaluate the posterior density of theta given a, b, n, and y by taking the prior, which is beta with shape a and b, multiply it by binomial likelihood with parameters n and theta, divided by the marginalized probability of y given a, b, and n irrespective of theta, which is this. Simplify some stuff a little bit, get a posterior distribution that is in the beta family with updated parameters a star and b star, where a star is a plus y and b star is b plus n minus y. And so this is a fairly rare case, which is known as naturally conjugate between the beta prior and the binomial likelihood. They have the same kernel, the part involving theta, so we can group some terms together, simplify this analytically, and it comes out in this case, although this is rare, the posterior distribution is in the same family as the prior distribution, but with updated shape parameters, a star and b star rather than a and b. And that's why it came out, the red line and the black line were on top of each other. Actually, the black line is correct, and the red line was from a finite number of simulations, but they correspond to the same concept, namely the posterior density of y given a, b, posterior density of theta given a, b, n, and y. And then with the posterior distribution of theta, we can obtain the posterior distribution of the vaccine effectiveness in green. If the vaccine effectiveness is like kind of a proxy for FDA's utility function, we can take the expectation of the green. So, you know, if this is the vaccine effectiveness and we have two decisions, either approve the vaccine or reject the vaccine, then we can, you know, get an estimate for how many people will die if we don't approve it, and, you know, the hospital bills and all that from the effectiveness of the vaccine. Question?
How will the posterior distribution change if we change it prior?
We'll get to that next.
Okay.
Other question? Everybody wants to know how it would change if we changed it prior. So let's do that. So instead of putting the prior on theta, which is kind of a weird intermediate quantity, but it's monotonically related to the vaccine effectiveness, let's put the prior on the vaccine effectiveness, which is the thing the FDA ostensibly really cares about for weird reasons, but we'll just accept those weird reasons. So let's put a normal prior on the vaccine effectiveness with mean equal to 0.3, standard deviation about 0.15. That would achieve what it is I said earlier, that it would be greater. So it's still kind of skeptical. At the prior mean, this would not be approved if it's 0.3. But it puts negligible probability on the vaccine effectiveness being negative. So negligible probability on the event that the vaccine causes you to get COVID. But it also avoids the problem that we saw earlier of not putting the prior mode basically so close to 1. Moreover, I would say what I'm proposing to do right now, put like normal prior vaccine around 0.3, would be more in line with what the scientific evidence showed up to 2019, where mRNA vaccines had an unblemished record of failure for 30 years previous. Now they failed by less and less each time. But the first time they didn't fail was in 2020. So it would have been entirely reasonable for scientists who study this sort of thing to believe, before seeing the randomized controlled data, that they were skeptical that mRNA vaccines would work, and they were more optimistic about more traditional vaccines, such as Johnson & Johnson or the one made by Oxford or something like that. So I would say that this prior would have been more in line with what scientists with expertise would have believed in mid-2020 before they saw the new data. So vaccine effectiveness prior much closer to 0. We do the same thing, well, pretty much the same thing. First, we need to truncate our prior so that no draws of vaccine effectiveness are greater than 1. That's impossible. But the way we've done it now, vaccine effectiveness is the primitive on which we express our beliefs about, and we monotonically map that to theta using a mutate statement, then simulate trials by a binomial distribution with success probability theta, filter based on what the randomized control data actually showed, plot based on the posterior distribution implied by the new and scientifically more appropriate prior that Pfizer should have used but didn't. Pfizer wanted, I think, to do ancient calculations because they believed that would be simpler. But in this context, ancient is not a virtue. We want to get this right. And we can get it right using modern computations fairly easily, like 5 lines of our code. What does it look like? Pretty much the same. This is the posterior density of theta, posterior density of the vaccine effectiveness. If you look extraordinarily closely, you might see that now the posterior mode, median, mean, whatever, might be high 80s rather than low 90s. But it is certainly way shifted from the prior on the vaccine effectiveness in black there. And so what I would argue is the value added of a Bayesian analysis is how much does it shift the posterior beliefs about the thing that you care about from the prior to the posterior as a result of having done the study where you collect data, whether it's a randomized controlled trial, observational thing, qualitative thing, doesn't matter. Conditional on the data, it shifts the distribution of the thing that you care about. How much it shifts is the value added of the study, particularly if you anchor the prior distributions to what the scientific community believes before you collected the data. And so this study by Pfizer, tremendously value added because it substantially shifted the beliefs about the effectiveness of mRNA vaccines from 30 consecutive years of failure to something that is really, really good. And so there's a lot of consternation, most of which due to the Fisher, about priors and how much they influence the analysis. Not nearly enough emphasis on how open-minded you have to be Bayesian. Okay? State your beliefs in black. Now you've put what you believe in. And if the data comes out like y = 8 on N94, then you got to update your beliefs a lot. But Fisher said, well, science as we knew it, or know it, or knew it in the 1920s, would be destroyed if we allowed researchers to input their beliefs about something. And so science would devolve into, this person believes this, another person believes that, whereas science is supposed to get at what is objectively true. And so in Fisher's view, if we allowed Bayesian stuff in science, it would destroy or undermine completely science. Conversely, you might say, particularly in retrospect these days, well, this was the most important scientific thing in the last 100 years, maybe. And Pfizer did it with Bayesian analysis. And did the world come to an end? No, it did not. It might have without the vaccine. But, they did the analysis. It was basically fine. Could have chosen a better prior, but that's not fundamental. And so what we really need as scientists is a mechanism to decide when and by how much we need to change our minds. So to take a subjective view about probability rather than the objective Fisher thing about like the true effectiveness. Yeah.
So in this case, the prior would be like some of the past trials that was being done for this vaccine, basically, and then.
Or not for COVID-19 because COVID-19 didn't exist.
That's true.
But they tried mRNA in a lot of other contexts since the 1980s.
Okay.
And it failed every single time. The first time they got it right was in early 2020, and not just BioNTech, but also Moderna got it exactly right with one take. But it's kind of unlikely that they would have gotten enough funding had there not been such an emergency in the United States and a bunch of other governments. It was called Operation Warp Speed or whatever in the United States, said we'll buy like 100 million doses. If it doesn't work, like keep the money, but here's the money now, and you can, try your best to develop it. They gave it to like 12 different companies or whatever. And honestly, only 3 or 4 got the approval ultimately. But 2 of them were the mRNA. And so the Bayesian view is, well, we need a mechanism to govern the process of changing our minds about when something is ineffective and when it becomes effective in order for science to advance. And so not only did Pfizer's Bayesian analysis not destroy life as we know it, Caitlin Carrico and her colleague, somebody named Wiseman, Dave Wiseman or whatever, won the Nobel Prize for developing mRNA vaccines. Caitlin Carrico is like the vice president of BioNTech. So other scientists gave the biggest prize in science to these people because they were the 2 people primarily responsible for changing the scientific community's minds about the effectiveness of mRNA vaccines. And now there's a lot of research in mRNA technology as to whether it could also be used for malaria, HIV, a variety of other viruses. So, you know, who are you going to believe, Fisher or the Nobel Prize Committee? Of course, things like the FDA didn't really exist in Fisher's time, so that might give him a little bit of an out. But certainly we're much better off, particularly in the countries that could afford it, to have mRNA vaccines, and the countries that got other vaccines were not as effective. They might have been more effective in actually getting it injected into people, but the vaccine itself, the mRNA vaccines were the most effective. Moreover, I would argue that this sort of thing, particularly if you do like point estimation, it's not really sufficient for you decide, well, should I make this available to like all adults, particularly if the government is going to pay for it, because that's going to cost hundreds of billions of dollars. So I don't want like a point estimate of the effectiveness. I want a distribution of the effectiveness so I could evaluate the G, where G would not really be vaccine effectiveness, but what's the cost benefit of this? Like, how much hospital bills am I going to save if like half the people get vaccinated versus, you know, it's going to cost $250 billion or whatever to get this to half the people. You know, I could calculate that expectation, like the profit or whatever of rolling it out. But I need a distribution to do that, and it's good that I get a distribution that's of the green that's so close to 1. Made it an easy decision. Should have been easy. All right, how much time we got left?
7 minutes.
Perfect. Let's do some bowling. So before we use this probability mass function, but this probability mass function we used last week is actually valid if 1 plus kappa is continuous instead of restricting it to be discrete. So now let's let the probability of knocking down x out of n pins depend on theta, where theta is any real number as a parameter. If theta is 1, this is going to specialize back to what we did in week 2 or week 3. If theta is 0, you can take my word for it that the probabilities get reversed as compared to if you use the same theta but give it a positive magnitude. So if theta is -1, you just like take all the probabilities and switch them around. So the probability of a gutter ball is about 0.28, and the probability of a strike is about 0.03, something, etc. And so now if you were to think about a prior for your personal theta, well, theta can be any real number. And the conditional expectation for how many pins you knock down on your first roll is a monotonically increasing function of theta. So we can think of theta as the bowler's ability. And like I said, this would be a more conventional way for actual Bayesian to set up a problem like this. But you could think in your case, well, if I expect to knock down like 6 pins, about 6 pins on my first roll of random bowling, I could go over to here, down to there. That might be the center of a normal prior on theta. But I'm a little bit uncertain as to whether my expectation is exactly 6 or whatever. So I have some uncertainty over here. It's going to be uncertainty on the curve. It's going to be uncertainty a little bit down here. So I can choose the standard deviation on my normal prior for theta to achieve something like that. So now, suppose we have a normal prior for the bowler's ability, represented by theta, has mean m, standard deviation s, where s is positive. The joint PDF of theta and x is going to be this normal PDF for theta multiplied by the conditional PMF for x given theta and n. N is the number of pins available to be knocked down. So the marginalized PMF of x irrespective of theta, but conditional on n, would take this expression, integrate theta out over the all real numbers of the joint PDF for x and theta. However, we cannot obtain the antiderivative to evaluate that area under this curve. And your mother may have told you you can do anything that you set your mind to, but the so-called Risch algorithm would say otherwise. It can prove that any function, or it can detect whether any function has a elementary antiderivative. What does elementary mean? Elementary means a finite number of terms involving basic operations like arithmetic, powers, logarithms, maybe trigonometry, the sort of operations you would have on your calculator app. If an integral can be done with a finite number of those operations, we say it has an elementary antiderivative. And the Risch algorithm is extraordinarily complicated, but it can say, does this integral have an elementary antiderivative? And if so, here it is. And if not, it's impossible with a finite number of terms. Like I said, we saw the beta thing, not elementary, because it had a product of an infinite number of terms, even though the terms were elementary.
Very quick question. What is the theta, like with the slash?
This is my notation for marginal
Okay.
x given n. I need to take the joint, integrate over theta. I'm left with a function of x and n
Okay.
alone.
All right.
So we can't do it. But we can plot it. So let's say m is a half, s is 2. We can have a function bivariate where we evaluate the normal density, multiply it by our probability mass function of x given theta. If x1 is 10, we get the black curve. If x1 is 8, we get the red curve. If x1 is 4, we get the green curve. So the Risch algorithm says, well, we can't do some elementary calculation to get the area under the black curve or the red curve or the green curve. However, we don't need an antiderivative to evaluate a definite integral. We could do like the little trapezoids thing to get the area approximately under the red curve, and a computer can do really little trapezoids. And if you just call the integrate function, which does numerical integration of that function from negative infinity to infinity, assuming x1 to be 8, you get the area underneath the red curve here, 0.08 to 999. So this is not symbolic. So you have to have a computer to do this, but it's not quite modern. It's more like medieval. This is deterministic, but you really couldn't have done it by hand. But you could do it the modern way rather easily. So I'll just show you the steps. Here I'll only do 1,000,000 because this kind of takes a while. But I make a tibble with R draws from a normal prior on theta. But since theta is continuous, I'm never going to get the same thing twice. So there's no value in grouping by. So really, I call row-wise, which is basically like group by, where every row is its own group because it has its distinct value of theta. Then I draw x1 by sampling omega size equal 1 for each row with probability depending on my realization of theta, and then ungroup to get the original data frames. And if I want to calculate the marginal probability that x1 is 8 irrespective of theta, comes out to be 0.083, indistinguishable from 0.08 to 999. So I could do this the fully modern way with simulations, and that is not exactly, but that's the essence of what this article from 1990 was talking about. saying we don't need to do hard integrals or impossible integrals, particularly the multivariate integrals, which are even more impossible than the univariate integrals. We can get by with simulations. And so if we wanted to graph the posterior density of theta, if we observe the first roll of a frame of bowling being 8, it would look like this in the black line here. So black line is posterior, red line is my normal prior on theta. Observing just one roll of data updates my beliefs about this bowler's theta from red to black. From normal to not exactly normal, but nevertheless posterior. Updating my beliefs about the bowler's ability, much the same way update my beliefs about the effectiveness of mRNA vaccines. Much the same way we can do this with any model and any data. And we'll start to learn about that next week. Out of time for today. I will post the first homework assignment tonight or tomorrow. It'll be due before class next week. There'll be email of the instructions and whatnot, but it will cover probability. And that's it.